So in this last part of the unit, we're going to be talking about RC circuits where there are resistors and capacitors in the same circuit. So the big thing that's different is there's time dependence in the circuit. It's not just steady state all the time. So let's take a look at this. You can see we've got currently this switch is at position A. So there's no charge on the capacitor. We have to know that ahead of time. There's no charge on the capacitor. So there's nothing that's going to make current flow around this system. So it's basically the voltage across the capacitor and the voltage across the resistor are both zero. We're going to switch at time equals 0. We're going to move that switch from A to B. Okay, so just after the switch moves, right, we remember that there's no charge on that capacitor. Charge can't move immediately. So the charge is continuous. The charge on the capacitor is about 0 still at the very instant after the switch is thrown. But the voltage across the resistor changes immediately. Why? Because there's no voltage across the capacitor. So if we do Kirchhoff's voltage law, going around in the clockwise direction, we go positive epsilon minus the voltage across R minus 0 equals 0. So the voltage across R has to be the same as epsilon. And then current is going to flow. We have a voltage difference of epsilon across that R, and so it's epsilon over R is going to be this current. That current's got to go somewhere. It's going to charge the capacitor. So as time moves on, you can see that the charge on the capacitor and the voltage on the capacitor increase because C equals Q over V. So those two things increase in parallel. And as the charge increases on the capacitance and the delta V across the capacitor increases, well, then you can sort of see that the difference of the potential difference across R will decrease, because as delta V across the capacitor gets closer and closer to epsilon, then the voltage difference across the resistor gets smaller and smaller. So as that happens, the current decreases. Eventually, delta V across the capacitor is equal to epsilon, and there's no current flow. We say that capacitor is fully charged. So in the steady state, the capacitance voltage is the same as the EMF, and Q is just going to be that voltage times C. So it's C times epsilon, C times the EMF value. A lot goes on there. Let's look at discharging. Discharging, we'll do it in the other direction. So it's all fully charged, it's steady state. Now what we do, and we know that the capacitor's potential difference is the same as the EMF, right, when it's fully charged. No current coming through the resistor. So the switch moves from B to A. What happens is the charge is continuous. Again, that charge can't leave the capacitor immediately. So the voltage difference across the capacitor is still delta V, which is equal to the EMF that had charged that up in the first place. And if you go around that circuit, remember now the EMF's not part of the circuit. So if we go around this circuit in a clockwise manner, we have voltage across the resistor has to equal the voltage across the capacitor. But note the polarity, right? The resistor, the right side of the resistor is connected to the top of the capacitor, and the left side of the resistor is on the bottom side of the capacitor. Alternatively, you can think that charge is going to flow counterclockwise through the resistor, and therefore for it to flow in that direction, we know that the right side of the resistor has to have a higher potential than the left side. It flows immediately, starts flowing immediately. The charge does not decrease immediately, but charge begins flowing immediately because there is a voltage across that resistor. So the current will be, at the very beginning, epsilon over R. As time goes on, the charge across the capacitor decreases, so the voltage across the capacitor decreases, and since there's only the capacitor and the resistor here, the voltage across the resistor decreases, so the currents decrease. And then eventually there's no charge on that capacitor. So the steady state, the charge, and the voltage at the capacitor are both 0. How do we analyze these? I want you to understand how these concepts work, because we really need to be thinking about what's true at the beginning, what's true at the end. The transition I'll take you through at some point here, but we really want to start analyzing how these individual values, charge, voltages, current, how they change. So let's look at this one. For a given variable, what's going to happen is we're going to know whatever the value is before the switch. Okay, that's really important in this case for the voltage across the capacitor and the charge. Okay, because the charge can't change quickly. What's the value immediately after you throw it? Well, for the charge, that would still be 0, right? For current, that'll change very quickly. So my initial value at t equals 0 plus, t equals 0 minus means just before the switch is thrown, t equals 0 plus means just after the switch is thrown. So that initial value gives you some information. And then we want to know what happens at t equals infinity. So this would actually be the graph for the charge, for a charging circuit. But the graph for current would be exactly the opposite. Start high and go down. And let's see how we do that. So here's the charge across the capacitor. What happens to the charge? We want to be able to graph this. We want to eventually be able to get a function for this. So it starts at 0, right? Before we threw the switch, it was 0. And it can't change instantaneously. That charge doesn't just immediately go off. It takes time to get the charge off those plates. So the charge, we knew the initial point, and we know the charge increases. And then eventually, again, once that voltage across the capacitor is equal to epsilon, it'll stop charging. Okay, so we know when it's charged, Vc is equal to epsilon, so Q equals C times epsilon, just using the equation for a capacitance. And there's that maximum there. So it's useful to know the starting point, the maximum, and we will know what the direction of those, and we'll be able to, logically infer what the shape of that graph is. What about current? When I switch that, before there was no current. When I switch it, it immediately has a current. Remember why? Because there's no voltage across the capacitor, so all of that E is across the resistor. So there's an immediate change in current. So it immediately goes up to E over R. And then as the charge builds up on C, as the voltage across the capacitor gets closer and closer to the voltage across the EMF, then the current decreases, so the voltage across R decreases. So this gives us the shape. And I eventually decreases to 0. And again, I'm not really saying asymptotically a lot, but these things all approach asymptotically. This is the overview for how we analyze these things. We're going to do a differential equation here, so it's going to be a lot. This is going to be a lot of math on this one. So if I go clockwise around the circuit, plus E minus I times R, current that's going through the resistor, times the resistance, minus delta Vc, the voltage across the capacitor. It's 0. So I'm going to rewrite this. First of all, Vc is just Q over C, the charge on the capacitor divided by the capacitance. Then I'm going to rewrite I in terms of Q. So now I have the beginnings of a differential equation here. That's a good differential equation right there. I want to separate out so I can integrate T on one side and integrate Q on another side. So I'm taking a step here. And by the way, I multiplied everything by C just to get that out of the denominator of Q over C. And then I'm rearranging, and I'm going to rearrange a little bit more. What I'm going to do is I'm going to divide by EC minus Q on both sides and multiply both sides by dt over RC. And then I'm going to integrate. Okay, so I'll let you look at that for a second to see what I did there. I want to get the Q's together. So in the previous line, I had EC minus Q on the left. I divide both sides by EC minus Q, and that gives me the dQ over EC minus Q. And then I take the other stuff to the other side. Multiply by dt, divide by RC. When I integrate this, excuse me, when I integrate this, on the right, I'm going to have T over RC and a constant. On the left. On the right, I have the log of EC minus Q, and I really needed a negative sign out there because if we talk about this as a U, du would be negative dq. So I need a negative sign out there. Then I'm going to do e to the left, e to the right, and I'm going to switch that negative sign over to the left. and you end up with this. E to the negative t over RC plus constant equals EC minus Q. And a little trick here is that left side, e to the negative t over RC plus K, is the same as e to the negative t over RC times e to the K. E to the K is just a constant, so I'm going to write this. It's going to be a different K, but this is the way I'm going to write it now. So it's equivalent to this. Now I'm going to rewrite it as just Q equals. There we go. That's not quite my final version of that, right? Because I can actually do better. I can find the K. In this case, right, I know the initial condition. I know the charge at the very beginning was 0. So what I can do is Q is equal to EC minus K times e to the negative 0 over RC. So that just ends up being minus K there. And I know at time equals 0, Q equals 0, so EC equals K. When I plug that, epsilon C in for K at the bottom of the previous column, then I can factor out epsilon C, and the final form ends up being Q equals epsilon C times 1 minus e to the negative t over RC. Okay, now visualize that. E to the negative t over RC gets smaller and smaller and smaller. So you've got this maximum thing. At the beginning, it's minus 1 minus 1, so it's 0. At the end, it ends up just being EC. So this Q ends up increasing monotonically. What we want to be able to do is look at a general approach to this, okay? We had this Q of t equals epsilon C times 1 minus e to the negative t over RC. When you see that term a lot, the variables are going to fit one of these two things. Q fits the one on the left. It's the max value times 1 minus t over RC. And you'll notice I have an asterisk in that variables will tend to fit either. I'm going to come back to that in a second. Alternatively, some variables, like in the case of current in a charging circuit, ends up being a max times e to the negative t over RC. It's a declining exponential. Okay? Now, when I said they'll fit this, that max, it really depends on the rest of the circuit. It might not go to or from 0. Okay, in other words, it might be a little more complex circuit. So we may have to do a little thinking about what the limits of this are. But this is the general shape that we're going to deal with. Now, how do we use that? One thing that's very useful is, of course we could plug in values. If you knew what the maximum value for something is, for example, for the charge on a capacitor, we knew that was going to be C times the value of the EMF. So we could plug that in there and we just do 1 minus e to the negative t over RC. If we know RC, we can figure out the charge at any given time. But one really handy thing is this thing called the RC time constant. And that's where when t is equal to RC, you have the maximum times 1 minus e to the negative 1. And e to the negative 1 is 0.37. So the way I like to think of this is that's how much it's changed from the, that's how different it is from the ultimate value. So on the left, we see this thing. If this thing is charging, if we subtract 0.37 from the max, that will be the value. In other words, we've gotten 63% of the way to our final value. And the same thing works in the other direction. If I start at some maximum value, like the current, and our equation is current max times e to the negative t over RC, after RC seconds, whatever that value happens to be, we are now 63% of the way from where we started to the final value. So that's 63% or the 37%, however you want to remember it, ends up being a really, really useful number.